This is SpaceTime, Series 25, Episode 55, for broadcast on the 16th of May, 2022. Coming up on SpaceTime, the first ever image of our Milky Way Galaxy's central black hole, the history and evolution of the Milky Way Galaxy, and countdown to the launch of the Boeing Starliner. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart-Gary.
Astronomers have unveiled the first ever direct image of Sagittarius A Star, the supermassive black hole at the centre of our Milky Way Galaxy. This historically incredibly important image, reported in the astrophysical journal Letters, was produced by a global research team of more than 300 scientists from 80 institutions around the world, collectively known as the Event Horizon Collaboration. The team used observations from a worldwide network of 8 radio telescopes, connected to form a giant interferometer the size of the Earth. Their work has provided overwhelming evidence that the object around which our entire galaxy revolves is indeed a supermassive black hole. Supermassive black holes, ranging in mass from millions to billions of times that of our Sun, are thought to inhabit the centres of most, if not all, galaxies. Scientists had previously seen stars orbiting around something invisible, compact, and yet very massive at the centre of our own galaxy, the Milky Way. This strongly suggested the object, known as Sagittarius A Star, was a supermassive black hole. But it's this new image which provides the proof. Sagittarius A Star is located 27,000 light-years from the Earth and has some 4.3 million times the mass of the Sun. Although we can't see the black hole itself because it's completely dark, glowing gas around it reveals a telltale signature, a dark central region known as a shadow, surrounded by a bright ring-like structure. The new image is actually capturing the light being bent by the powerful gravity of the black hole. Event Horizon Telescope Collaboration Project scientist Jeffrey Bauer from the Institute of Astronomy and Astrophysics in Taipei says the team was stunned by just how well the size of the ring agreed with predictions from Albert Einstein's theory of general relativity. These unprecedented observations have greatly improved science's understanding of what happens at the very centre of our galaxy, and it offers new insights into how these giant black holes interact with their surroundings. These latest observations follow the collaboration's 2019 release of the first ever image of a black hole, which was observed at the centre of the distant galaxy Messier 87. And the two black hole images do look remarkably similar, even though our black hole is more than 1,000 times smaller and less massive than that in M87. It's an important point because it tells us that general relativity governs these objects up close, and any differences we see further away must be due to differences in the material that surrounds the black holes. Imaging the Milky Way's black hole was considerably more difficult than for M87, even though Sagittarius A Star is much closer. You see, gas in the vicinity of the black holes moves at the same speed, nearly as fast as light. And that's true for both Sagittarius A Star and M87. But that's where the diameter, the Schwarzschild radius, comes in. The gas takes days to weeks to orbit around the much larger M87, while in the much smaller Sagittarius A Star, it completes an orbit in just minutes. This means the brightness and pattern of the gas around Sagittarius A Star was changing rapidly as the collaboration was observing it. Think of it as trying to take a clear picture of a puppy or kitten that's chasing a ball. In fact, the research team needed to develop sophisticated new tools to account for the gas movement around Sagittarius A Star. While M87 was an easier, steadier target, with nearly all images looking the same, that was certainly not the case for Sagittarius A Star. The final image of the Sagittarius A Star black hole is actually an average of the many different images the team extracted, finally revealing the giant lurking at the centre of our galaxy for the very first time. The collaboration worked rigorously for 5 years, using supercomputers to combine and analyze their data while compiling an unprecedented library of simulated black holes to compare with observations. One of the important things about all this is that we now have two very different sized black holes, and that offers an opportunity for scientists to understand how they compare and how they contrast. In fact, astronomers have already begun using the new data to test new theories and models of how gas behaves around supermassive black holes. Now, this process isn't yet fully understood, but it's thought to play a key role in shaping the formation and evolution of galaxies. This report from the European Southern Observatory.
Imaging a black hole seems like an impossible dream. After all, they are black and do not emit light. So how can we see them? Well, with a telescope big enough, we could at least see the immediate surroundings of the largest black holes. The supermassive ones that are millions or even billions of times heavier than our Sun. Then we would be able to unveil some of the mysterious secrets these monsters hide. Except that when you do the maths, you find that to observe even the closest supermassive black holes, you'd need a telescope the size of the Earth. Something beyond our wildest dreams. Or maybe not. A few years ago, 300 astronomers from nearly 80 institutes across the globe joined forces and found a way to create a telescope as large as our planet. And they did it without using new mirrors, screws, or steel. Their Event Horizon Telescope, or EHT, is not a real telescope, but a virtual one. The stroke of genius of the EHT collaboration was in using powerful radio telescopes that already exist, including ALMA and APEX, co-owned by ESO. They combined their observations in a way no one had ever attempted before, with a technique called very long baseline interferometry. This may sound like sci-fi, but it actually works, as the EHT team showed back in 2019. That's when they revealed the supermassive object at the center of the M87 galaxy to the world. The very first image of a black hole. To understand exactly how hard that was, let us drop in some facts. First of all, you should know that the EHT telescopes could not see the black hole itself, as it is invisible. Rather, they picked up the radio signals from the hot glowing gas around it and imaged the shadow the black hole casts on it. To do this, the telescope antennas in the EHT array had to be pointed to exactly the same position in the sky at exactly the same time. The EHT can tell if one of these antennas is off by just a millimeter, and if the timing is shifted by a trillionth of a second, even though the telescopes are located thousands of kilometers apart. Imaging the black hole in M87 then required combining the observations of all telescopes in the network using interferometry. This technique works best if you have many telescopes, which wasn't the case. The team had 8 observatories, though now the network has grown to 11. So the EHT researchers had to develop special algorithms to be able to fill in the gaps and reconstruct their image. It was like staring at a puzzle with most pieces missing, trying to figure out what the whole image would look like. To determine if the result was scientifically bulletproof, they used a variety of methods. Computer simulations to identify errors introduced by their telescope network, different teams working in isolation on reconstructing the image in different ways, new techniques and software. It took years of work until they were sure they had done it right. Only then did they show their image to the world. The result was like peering at the black hole in M87 with a telescope almost the size of the Earth, an instrument so powerful that it could see details as small as a donut on the moon. So what's next for the EHT? The team have already pointed their telescopes to a new target, Sagittarius A Star, the supermassive black hole at the heart of the Milky Way, our black hole. Sagittarius A Star is much closer to Earth than the supermassive black hole in M87. so you may think that imaging it is a piece of cake by comparison. Sorry to disappoint you. It's even more difficult. First, the center of the Milky Way is obscured to us by clouds of dust and hot gas that scatter the radio signals coming from around the black hole. Furthermore, because Sagittarius A Star is about 1,500 times less massive than its cousin in M87, its radio signals change far more rapidly in time. Blobs of plasma orbit it in just a few minutes, whereas those in M87 orbit the black hole every few days. This forces astronomers to adapt their algorithms and to develop new techniques to get stable images. A bit like trying to read the brand on a basketball while spinning it on your finger. In the end, the EHT team did manage to overcome all these obstacles. The first image of Sagittarius A Star, the black hole at the center of the Milky Way.
This is SpaceTime. Still to come, the history and evolution of the Milky Way Galaxy, and NASA and Boeing have set May 19 as the potential launch date for the long-delayed Starliner mission to the International Space Station. All that and more still to come on SpaceTime. A new study exploring the formation history of the Milky Way is also revealing new details about the dark matter halo enveloping the galaxy. The findings, reported in the Astrophysical Journal, is telling scientists more about our origins and providing fresh clues about our ultimate fate. The Milky Way has grown to be one of the largest galaxies in our part of space through a process called galactic cannibalism. This involves the Milky Way merging with and consuming smaller galaxies. And there have been lots of them. Astronomers have been able to identify and study 12 stellar streams within the halo of the Milky Way. These are the shredded remains of neighboring small galaxies and star clusters that have been torn apart and consumed by the Milky Way. In the process, the astronomers have identified areas containing higher concentrations of a mysterious invisible substance known as dark matter. Scientists have no idea what dark matter is. They only know it's there because they can see its gravitational influence on normal matter, such as preventing galaxies from flying apart as they rotate. They've calculated that dark matter makes up roughly 85% of all the matter in the universe. The rest, the remaining 15%, is composed of ordinary baryonic matter, the stuff that makes up the molecular gas clouds, stars, planets, moons, trees, houses, cars, and people that we see in the world around us. But so far, gravity appears to be the only way that dark matter interacts with normal matter, so identifying it remains beyond science's ability, at least for now. So, knowing where dark matter resides may provide scientists with more clues about its properties and composition. One of the study's authors, Professor Grant Lewis from the University of Sydney, says the properties of stellar streams are revealing the presence of dark matter. He says, think of a Christmas tree. On a dark night, you'll see the Christmas lights, but not the tree they're wrapped around. Still, the shape of the lights does reveal the shape of the tree. And it's the same with stellar streams. Their orbits reveal the dark matter. As well as revealing the dark matter holding stars in their orbits, these stellar streams are also telling astronomers about the formation history of the Milky Way, revealing how it's steadily grown over billions of years by shredding and consuming smaller star systems. The observations are all part of a dedicated program known as the Southern Stellar Stream Spectroscopy Survey, or S5, which is designed to measure the properties of these stellar streams. Lewis and colleagues are using the 4-metre Anglo-Australian telescope at the Siding Spring Observatory in rural New South Wales to measure the speeds of these streams and the composition of the stars in the streams so as to better determine their course and where they were born. But unlike previous studies, which have only measured the properties of one stream at a time, the unique capabilities of the Anglo-Australian telescope has allowed astronomers to study multiple streams at once. The research gives astronomers a sort of snapshot of the Milky Way's feeding habits, such as what kinds of stellar systems it likes to eat. And a crucial ingredient for the study has been the wealth of additional data supplied by the European Space Agency's Gaia mission. Gaia has provided the authors with detailed measurements of the positions and motions of stars, helping to identify those that are in stellar streams. Now, the streams themselves can come from either disrupting galaxies or star clusters. And these two types of streams are providing different insights into the nature of dark matter. One of the key questions the authors want an answer to is the role dark matter played in the birth of the Milky Way Galaxy itself. See, many astronomers see dark matter as a kind of scaffold upon which the large-scale cosmic web-like structure of the universe is draped. Lewis says the team will continue to gather observations and measurements of stellar streams throughout the galaxy.
This is a relatively new program that we started only a couple of years ago now. So what we've realized, of course, is that our Milky Way galaxy has grown by eating smaller systems that fall in. So a little galaxy or a globular cluster falls in, the gravity of the Milky Way tears these objects apart. And for a long time, people have searched for signs that these streams are out there, but they tend to be very, very faint. They're very difficult to find. Over the last decade or so, people have been surveying the sky to really big, deep depth, and these streams are starting to be uncovered. So our program grew out of something that's known as the Dark Energy Survey, which is trying to measure the expansion of the universe to try and work out what dark energy is. But in looking out into the distant universe, you also see the nearby universe, and a whole bunch of these streams were found on the sky. So seeing the streams is one thing, but what we wanted to do was measure the speeds of the stars in the stream, because if you can reconstruct the orbit of the stream, you can work out what's pulling it apart, what's the gravitational potential look like, and that reveals the dark matter content of our Milky Way galaxy. That's the dominant mass that's out there. So this survey, the Southern Stellar Spectroscopic Survey, we have been doing this sort of systematic search for the properties of these streams, and we now have 12 of them, which is what we've just published. But we're still taking more data, and we're collecting, more orbits and more streams to try and reveal the underlying dark matter. Once we have a good idea of roughly how much dark matter is out there in the Milky Way, right, and it dominates by a large factor, we don't know the details, right? We don't know if the dark matter is distributed like a spherical football, or is it shaped more like a rugby ball? Is it smooth? Is it clumpy? And different ideas for what dark matter is have different predictions for precisely the kind of distribution of dark matter that's out there. So it's only really with these streams that are traveling through our immense halo that we are able to sort of piece together the picture of not only how much dark matter is out there, but just how it's distributed.
Am I likely, by cupping my hands together, to snag a piece of dark matter in my hand? Or is it more likely that it's in a halo surrounding the galaxy, but not infused in the galaxy?
No. The name halo is a bit of a misconception. The actual density of dark matter in our galaxy, it's a very badly named thing, the halo, right? But the density actually increases towards the center. So there's actually more dark matter here than there is in the outskirts. So what you said, when you cup your hands together, there is dark matter in your hands. It's actually, dark matter that holds the sun in its orbit. It has a very big contribution to making the sun orbit the Milky Way galaxy. So it depends on precisely which idea of dark matter we're thinking about. But you might have 10 dark matter particles inside your hand. Now, on the scale of the Earth, where we're sitting here, where there are, uncountable numbers of atoms in the air, dark matter is relatively irrelevant to you. But when you add up the amount of dark matter that's out there and realize that it's not in a flattened disk like the Milky Way, but it's more spherically distributed, then that's when the overall effect of dark matter comes into play.
So we know that in the interstellar medium, there's 0.5 atoms per cubic centimetre. So dark matter is a lot smaller than that, much less.
Oh, yes, as individual particles, but the cumulative effect of it is much more, right? So again, on a little region, you don't have to worry too much about the dark matter, but when you get to the scale of roughly the size of the galaxy and beyond, then dark matter dominates.
And yet we still have no idea what it is. We think it's wimps rather than machos, but other than that...
Yes, it is an embarrassment at some level. The problem is, of course, is that we know the effect of dark matter is its gravitational influence. We can detect that. But if you really want to work out what dark matter is, you want it in the laboratory, and you want to be able to look at it under a microscope and, put it in a magnetic field and work out its properties. It just ignores all of that stuff. So we do have some experiments set up where people are looking for possible rare interactions of dark matter with normal matter. And there's this experiment that's going in STOR, which is looking for this direct detection. Our experiments just have not been sensitive enough to see anything. But on the flip side, this means it's been an absolute fairground for theoretical ideas. So in terms of proposed possibilities for what dark matter is, what kind of particle, and where does it fit into the zoo of fundamental particles. There are pages and pages and pages written on those, but we are really lacking the experimental evidence to tell one form of dark matter from another.
The 12 streams that you've been studying, that must be exciting in itself, because you're finding out here about the building blocks which made the Milky Way. Did these include things like the Magellanic Bridges and also the movements of Canis Major Dwarf and Sagittarius Dwarf, or are these 12 different streams?
So these are 12 individual streams themselves. So they've come from separate objects, and they've got various names: Orphan, Cheneb, Indus. They've been given these names. They're out there in the halo, and we are catching them at a certain point in their destruction, right? So if we were observing them a couple of billion years ago, we'd have seen them as like individual dwarf galaxies or globular clusters. In a few billion years, the action of the gravity of the Milky Way will ground these things down, and their stars will be just distributed through the halo. They do inhabit the halo with other objects, though. You mentioned the Magellanic Clouds there, and of course the Large Magellanic Cloud is actually quite a big galaxy, big dwarf galaxy. And so we have to take into account the influence, the gravitational influence of the Magellanic Cloud on these streams' orbits. These things, they actually feel each other's gravity as they travel around in the halo. So that's what we're trying to do, is put together this comprehensive picture of how these things are being ground down. And it will tell us what's going to happen to something like the Large Magellanic Cloud, right? So Sagittarius is, again, it's a largish dwarf galaxy that's being ripped apart. Its stars completely litter the sky, and again, in a few billion years, it's going to completely disappear.
Yeah, it's crashed into the Milky Way a couple of times now, hasn't it?
Absolutely, and it's crashing into the disk on the other side of the galactic center. Basically, right now, it's on its way through. Now, some people think that the Large Magellanic Cloud is only just starting this journey, right? It might actually be on its first real path of the Milky Way. Yeah. But in working out what the dark matter distribution is, that will tell us whether it's going to escape, is going to go back out to larger distances, or is it now doomed? Is it essentially like on its death spiral? It's on its way in, and in a few billion years, it too will be seriously torn apart by the action of the Milky Way.
When you look for stellar streams, you're looking at the individual stars and their movements, and Gaia's helping you with that, the European Space Agency satellite. And there's also the composition of these stars. They're a little bit different to the bulk stars in the Milky Way, aren't they?
Yes. So when we use the Anglo-Australian telescope up at Coonabarabran, we get a spectra of light of the stars, and we can use the Doppler shift to tell us how fast they're moving. But we can also use the distribution of lines to tell us the chemistry of the stars. And that's very important because it tells us where those stars have lived their lives. So if you think about a star like the Sun, which has been in the Milky Way for its entire lifetime, it was formed out of material which basically been in the Milky Way, and there have been several generations of stars, and each generation basically pollutes the next generation with chemical elements because that's what stars produce. For these streams, though, they were born in smaller systems, so they don't really have the vigorous kind of star formation that we see in the Milky Way. And in fact, in some of these objects, right, they are so small that it takes just essentially one supernova to blow away a lot of the gas that makes the next generation of stars. So we tend to see that these streams are made of stars which are chemically poor, that they are less enriched than the stars that we would see in the Milky Way. And that, as I said, that's an important clue to where these stars came from. And also, importantly, it tells a bit about how big the progenitor was before it fell into the Milky Way.
So we look for something called metallicity.
Any element heavier than helium is a metal to an astronomer. So when we see these elements, it's known as metallicity. For the stars that we look at, the primary elements that we see are the lines from calcium. So there's a particular set of lines called the calcium triplet, which gives us a good measure of the velocity through the Doppler shift, but also the amount of calcium is related to the overall abundance of elements, especially iron. So we can use that as a measure of how chemically enriched the stars are.
And by looking for a whole bunch of stars that are similar in that respect, that are moving through space in the same general direction, that lets you know they probably started out in the same place, and that's a stellar stream.
Absolutely. Yeah, so, we collect a lot of information on not just the stars. So we have an idea which stars are probably in the stream, and then we go to the Anglo-Australian telescope and we observe all of those stars that we can see, and then we can use the chemistry and the velocity and also, as you mentioned, the motions from Gaia to isolate the stream so we really know that they are stream members. It's a little bit of whittling down your sample. There's a lot of stars on the sky, and you have to then isolate the ones you think are in the stream and then follow them up, etc. So we can be confident that we are really seeing individual streams.
Have we decided yet whether globular clusters are in fact the cause of other galaxies, or are they still things that may have been created in stellar nurseries within our own galaxy?
You know what? That's the kind of talk that can get you into a pub fight with certain people. We really don't know. In fact, the picture is becoming more confusing rather than less. It's probably a little bit of column A, a little bit of column B, that some globular clusters were formed in situ and the Milky Way formed. Others have definitely been brought in associated with some of these objects that have fallen in, and some of them do appear to be the stellar cause of reasonably chunky dwarf galaxies. But there's no clear picture, and there's a completely separate discussion about what we're seeing in our next door galaxy, the Andromeda Galaxy, that, again, just makes the picture messier. So I would say that we don't really know yet.
Well, luckily, the Andromeda Galaxy picture will get clearer over time as it gets closer.
It's definitely going to get clearer as it gets closer, but I'm just sort of hoping that we can work out what's going on a little bit in my lifetime rather than having to wait 3 to 4 billion years.
When you look at the halo, you're seeing some of the very oldest stars in the galaxy as well. Is there a reason, do you think, why so many really, really old stars, we're talking about stars that our population too may be made of the original material from the original stars. Have we worked out a reason why there are so many old stars in the halo region?
So there's a mix of reasons. So firstly, the stars that were formed there, if you can imagine, the Milky Way used to be more spherical when it was first born, and the first stars were basically born out there in this roughly football shape. And then the gas collapsed down to form the stellar disk that we can see in the Milky Way. The stars that were then left out there, of course, they were essentially left on their own, right? They were individual stars more or less wandering around. And when they die and explode, etc., their material can't really get recycled because there's just so few stars out there. So there will be some stars that were born in situ in the original halo of the Milky Way. But a lot of them as well, the stars that we can see out there, they are objects like these dwarf galaxies that fell in a long time ago, and they've been completely disrupted and added to the distribution of stars that we can see in our halo. And because they came from smaller systems, they tend to be chemically poorer. And so there's been this mix of the very oldest stars that were formed in the Milky Way, plus additional older stars that basically grew in environments where there wasn't much star formation. So yeah, it's a messy, complex picture exactly how a galaxy grows. But we think it's been this ancient accretion plus some stuff formed at the very earliest epochs.
That's Professor Grant Lewis from the University of Sydney. And this is SpaceTime. Still to come, the countdown underway for the launch on May 19 of the new Starliner spacecraft. And later in the Science Report, a new species of theropod dinosaur discovered in Argentina. All that and more coming up on SpaceTime. NASA and Boeing have announced May 19th as the potential launch date for the long-delayed Starliner spacecraft. Starliner was meant to complement SpaceX's Dragon, providing crew transportation services to and from the International Space Station as part of NASA's Commercial Crew Program. But while Dragon's now undertaken 6 manned space flights, including 5 for NASA and 1 for Axiom to the International Space Station, and another carrying a group of space tourists into orbit, Boeing's Starliner has been struggling with technical issues. Their one unmanned orbital demonstration test flight back in December 2019 failed to reach the space station because of a mission clock error, triggering an early orbital insertion burn, which resulted in the spacecraft entering orbit too low. Mission managers then found a software error that would have prevented docking even if the spacecraft had reached the orbiting outpost. And Starliner almost failed to make it back down to the ground as well. That's because of another software issue which would have caused the capsule and service module to crash into each other during the return to Earth. Luckily, that problem was discovered and rectified at the last minute. But all in all, it's not been a good start for the Starliner. An attempt at a second unmanned demonstration mission in August last year was scrubbed after corrosion was discovered in 13 propulsion system valves due to moisture from passing thunderstorms interacting with the propulsion system's nitrogen tetroxide oxidizer. And the issue was deep inside the spacecraft, meaning it would need to be disassembled back in the hangar in order to reach the problem. Now, if all goes well, this week's Orbital Test Flight 2 will finally get off the ground on top of an Atlas V rocket from Space Launch Complex 41 at the Cape Canaveral Space Force Station in Florida. As before, the mission is designed to travel to the International Space Station, carrying supplies and undertaking a fully automated docking. Later, the spacecraft will undock automatically from the space station. It'll then hold station for a while off the space station before finally moving off, undertaking a deorbit burn, jettisoning its service module, and undertake a fiery return to Earth before releasing a parachute and landing at the White Sands Missile Range in New Mexico. Now, based on data from that May 19 test flight, a manned test flight could happen before the end of the year. And only if that goes well, Starliner will finally join Dragon in undertaking regular crew transfer duties to the space station, a mission which has now been made far more vital because of the ongoing issues with the Russian Federal Space Agency Roscosmos in the wake of Russia's invasion of Ukraine and subsequent human rights abuses. This is SpaceTime. And time now to take a brief look at some of the other stories making news in science this week with a science report. A new study warns that climate change will cause an increase in the transmission of new and existing virus species between animals and humans. The findings, reported in the journal Nature, are based on a study looking at the movement of wild animal populations around the world because of climate change, which is predicted to lead to at least 15,000 viral transmissions between species by 2070 under the 2 degrees Celsius warming scenario. The authors found that as animals move into new areas driven by climate change, they'll often encounter other species for the first time, in the process creating new opportunities for viruses to jump from one species to another. The risk of viral transmission from wild animals to humans is highest in areas of high human population density, such as tropical Africa and Southeast Asia, and it could lead to a raft of new and emerging diseases. A new study has concluded that 7 hours is the ideal amount of sleep for people in their middle age and upwards, with both too little and too much sleep associated with poorer cognitive performance and mental health. The findings, reported in the journal Nature, are based on a study of over 500,000 people aged between 35 and 73. Sleep plays an important role in enabling cognitive function and maintaining good psychological health. It also helps keep the brain healthy by removing waste products. As people get older, you often see alterations in sleep patterns, including difficulty in falling asleep or staying asleep, and decreased quantity and quality of sleep. It's thought that these sleep disturbances may contribute to cognitive decline and psychiatric disorders in the aging population. So researchers looked at sleeping patterns, mental health and well-being, and cognitive performance. Brain imaging and genetic data were available for almost 400,000 people in the study. By analysing these data, the team found that both insufficient and excessive sleep duration were associated with impaired cognitive performance, such as processing speed, visual attention, memory, and problem-solving skills. Paleontologists have identified a new species of giant megaraptorian dinosaur based on fossilized remains found in Argentina's Patagonia region. The 70-million-year-old theropod, named Macrothorax, was around 10 meters long and weighed some 5 tons. Megaraptorians are a group of predatory dinosaurs that inhabited Australia, Asia, and South America during the Cretaceous period. The new discovery, reported in the journal Scientific Advances, is based on a partial skeleton found at a dig site in southwestern Santa Cruz province. UFO sightings during the height of the Cold War and following the infamous Roswell incident in 1947 triggered the US Air Force to launch what it called Project Blue Book, a formal investigation by the Pentagon into claims of flying saucers and other paranormal phenomena. Project Blue Book had 2 goals: to determine if UFOs were a threat to United States national security and to scientifically analyze UFO-related data. The investigations ran from March 1952 through until December 17, 1969, and were undertaken by a team of astronomers and Air Force aviators. By the time Project Blue Book had ended, it had collected more than 12,618 UFO reports, and it concluded that most of them were misidentifications of conventional aircraft or natural phenomena such as clouds, stars, or the planet Venus. The study concluded that the investigation of UFOs was unlikely to yield any major scientific discoveries. Nothing that was found represented technological developments or principles beyond the range of existing modern scientific knowledge, and the investigations yielded no evidence of any threat to national security. Also, there was no evidence that sightings categorized as unidentified were extraterrestrial vehicles. And of course, years later, the National Reconnaissance Office confirmed that many reports were actually flights by the former top-secret U-2 spy plane, as well as the A-12 and SR-71 Blackbird reconnaissance aircraft. Still, 701 reports were classified as unexplained, even after analysis. Ultimately, Project Blue Book found that UFO sightings were generated as a result of a misidentification of various conventional objects. Some were a mild case of mass hysteria. There were also individuals who fabricated such reports to perpetuate a hoax or seek publicity, and of course, people suffering from psychological issues. But Tim Mendham from Australian Skeptics says now, thanks to pressure from UFO groups, a new Pentagon investigation into unexplained aerial phenomena is being launched.
Yeah, that's right. And there's some suggestions that vested interests in the UFO field have been very influential in getting this Pentagon investigations up and running. The trouble is that Pentagon investigations are often sort of implemented or set in motion by politicians who are not necessarily known for their great scientific acumen. And so if a lot of UFO proponents who are very active, very sophisticated in their marketing impact, are suggesting that the Pentagon should be looking at these things, then it sometimes happens, and the Pentagon has been asked to look at, through recent legislation, just at the end of last year, to have a 4-year project to investigate unidentified aerial phenomena, etc. Now, the thing is that this is based on the fact that these famous recent Navy videos that were sort of released showing various artifacts in the sky, which have been debunked very quickly, but they received a lot of publicity, and because the Pentagon said these are genuine recordings, does not mean they are genuine things, or at least not
the
things. The
recordings are real, but the interpretation is open.
Yeah,
to debate.
exactly. But the people only got as far as the recordings are real, and therefore they assumed that meant the things that they had recorded were actually real UAP or UFO phenomena. They aren't. So that was taken up by the UFO community as endorsement, and then the investigation of those particular videos said, and a lot of other UFO sightings said, we can't say what they are. And naturally, because they didn't outright debunk a lot of these things and say, this is a balloon, this is Venus, this is whatever, to the UFO committee, that meant endorsement, that the Pentagon was saying they're real. No, No. They were just saying they can't say what they are, and we have to leave it at that. And that's true of a lot of UFO sightings. I mean, the small percentage of UFO sightings that you can't instantly put down to known phenomena like Venus and like balloons and like misunderstanding of meteorological phenomena, there is a percentage there that you can't explain it, and you have to leave it at that, really. You don't have evidence for UFOs from things you don't know what they are. That's a big jump to move from don't know to I do know, and it's a UFO. So that's what the Pentagon was doing. They're having a lot of things saying they don't know what they are, and the UFO community jumped on that and said, here, proof. But no, it's not. It's just don't know, and you leave it at that. But the UFO community then took that and they heavied the powers that be into saying this should be looked at again, as you say, Project Blue Book, which ran for how long? 20 years? More than 20 years? A long time anyway, to try to look at the evidence that was being put forward then. It's just a new generation of that, a new variation on a theme.
But Project Blue Book was really about making sure the public had their minds elsewhere rather than on the truth of the whole thing, which is that there was a bunch of military black book projects.
Yeah, I mean, whether it was by the American military or Russians or whatever, it was also a period of Cold War mentality and a Cold War paranoia. So there was a lot of sort of background noise there that actually made it worthwhile doing. But yeah, if they were investigating UFOs to take people's mind off that they were actually military things, and that it didn't necessarily work because people have used it as it's military technology, secret military technology, rather than anything from outer space. But the UFO community still wants it to be from outer space, so they're convinced that there's something out there that should be investigated, and the powers that be will put aside 4 years of some poor sods who will then wade through all the sightings, etc., and trying to see if there's anything interesting. I can predict, using my psychic powers, that after 4 years we won't be any closer to definitive proof that UFOs are real, or unidentified aerial phenomena represent extraterrestrial craft. It's going to be just another exercise that you're saying, whether it's placating the UFO community or not, I don't think we're going to reach any concrete conclusions out of it. The same way as the Pentagon hasn't about the current set of sightings that we recently discussed, which are pretty old actually. Most of those videos were about at least 10 years old. They were just having to be released recently. So there's the UFO community pushing hard to get this stuff investigated. Pentagon was saying, politicians wanted to investigate it, so we'll investigate it. I don't know how seriously they'll do it, whether they see it as a nice, handy alternative to real military technology they don't want people to know about. We'll just see. And I predict not a great outcome.
That's Tim Mendham from Australian Skeptics. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuart-gary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuart-gary.com for full details. And if you want more space time, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTimeWithStuartGary. And SpaceTime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.